Okay, so before we start magnetic fields, you have to be able to show all three dimensions. This is the only chapter all year where you're going to be thinking and doing problems three-dimensionally. So on a piece of paper, it's no problem doing 2 dimensions, but your third dimension is going to be into the page and out of the page. So to show into the page, you draw an X. X indicates in, and then a dot indicates out. And the reason we use X's and dots is because if an arrow, it's all based on an arrow. If an arrow is traveling away from you, as it travels away from you, you see the tail feathers on the back of the arrow. Kind of looks like an X. So that's in. And then if an arrow is coming at your face, you're going to see a dot, which indicates out. So you can use X's and dots for anything that's a vector. You could use this for velocity. You could use it for acceleration. You could use it for force. You could use it for magnetic field. All right, so let's talk about magnetic fields. So first off, the symbol for magnetic field, I think it comes from a Latin word, to be honest. I'm not totally sure. The symbol for magnetic field is B. So see down here in this equation, we got, F equals QVB. B indicates magnetic field. The unit for magnetic field is the Tesla, like the car company. Or you may remember the hairdo band from the 80s. Well, you guys weren't alive in the 80s. But anybody know the band Tesla? Yeah? So they've been around for a long time. So Tesla, so let's see what else. Now, this chapter breaks down into 2 major ideas. So in this lecture, we're going to be focused on the first major idea. Tomorrow, we'll talk about the second major idea. But the first major idea is this. What do magnetic fields do? That's the first major idea for magnetic fields. What do they do? And then the second major idea, which we're not going to talk about today, the second major idea is, where do magnetic fields come from? All right, so that's for later. Now, the first question, the first major idea, what do magnetic fields do? Well, right here. Magnetic fields exert force on moving charged particles. Hey, what else exerted force on charged particles? Electric fields. And just notice here, in order for a magnetic field to exert a force, the charge must be moving. If the charge is at rest, it's not going to get a force. All right? So the second thing here, the equation for calculating the force of a magnetic field on a moving charged particle is this. So this would be force of magnetic field, but FB. B for magnetic field. The force of a magnetic field is equal to QVB sine theta. Q is charge, measured in coulombs. V is the velocity of the charged particle. So if that velocity is 0, the force is going to be 0. So the charge moving in the field, it has to have a velocity. Okay? B is the strength of the magnetic field, measured in Tesla. And then the trickiest part of the equation is this theta right here. So theta is defined as the angle between the magnetic field and the velocity of the charged particle. It's the angle between the magnetic field and the velocity of the charged particle. So I have my arrows here. So if you're watching this lecture at home, it's going to be hard. This is not going to really apply on the screen. So here's what I have. I have 2 arrows, and I'm going to use this to show you what I mean by this theta. So let's say that this red vector here, this red arrow, represents the magnetic field. Okay? So if the magnetic field is traveling towards that wall, and then the charged particle is traveling towards the window, what would be the angle there? 90 degrees, right? If the magnetic field is traveling this way and the charged particle is traveling this way, the angle between the magnetic field and the velocity of the charged particle would be 90 degrees. And I just want to point out something. What is sine of 90? 1. Sine of 90 is 1. That's maximum force. That's max force. Now the other extreme would be sine of 0. What is sine of 0? 0. Or 180. Sine of 180 is also 0. So that would be minimum force. Okay? So sine of 0 would be like this. Magnetic field is traveling towards the back wall. The charged particle is traveling towards the back wall. If they're both traveling in the exact same direction, what's the angle between the magnetic field and the charged particle's motion? 0. In this situation, can the magnetic field exert a force on the moving charged particle? Nope, because the angle between them is 0. Does that make sense? Okay, and then 180 would be this. Magnetic field traveling that way, charged particle traveling the other way. You know, that'd be the exact same thing. The force would be 0 there. So in order for the magnetic field to exert a force on the charged particle, the magnetic field and the charged particle have to cross. There has to be some angle there. And then when does force become a maximum? 90. At 90, when they cross like that. Okay? All right. Third idea here. The force that the magnetic field exerts on the moving charged particle will always be perpendicular to the magnetic field and the velocity. So here, this gets a little bit tricky. So say like, you got, here's your magnetic field. This represents magnetic field. This represents velocity. Remember from geometry, 2 lines make a plane? Does that ring a bell? All right, so if you have 2 lines like this, 2 lines intersecting form a plane. The force of the magnetic field will always be perpendicular to this plane. So if you take your magnetic field and the velocity of the charged particle, just draw them out as 2 vectors, the force will either be perpendicular this way or perpendicular that way. But it'll always be perpendicular to this plane that's created by B and V. Does that part make sense? It'll always be perpendicular. Now, how do we figure out if it's going to be perpendicular this way or perpendicular the other way? Because there's 2 possibilities here. It's either going to be perpendicular to this plane pointing that way or perpendicular to this plane pointing the other way. So to figure out which way the force is, that brings us to our last idea for today, which is right-hand rule number 1. So first off, right-hand rule number 1. Oh, just the fact that we say right-hand rule number 1 implies that there's a right-hand rule number 2. And remember, like I said at the beginning, there's 2 major ideas. Did I talk about that? Yeah. There's 2 major ideas in this chapter. The first idea is what do magnetic fields do? The second idea is where do magnetic fields come from? Okay, so right-hand rule number 1 goes with major idea number 1. Right-hand rule number 2, which we're not doing today, goes with major idea number 2. So here's how you do right-hand rule number 1. Right-hand rule number 1. So everybody put the right hand up. Your 4 fingers are the magnetic field. And that's kind of easy to remember because if you hold your hand sideways, your fingers here kind of make the shape of a B. You ever see? That's how I first learned it, right? You guys see it? Like gotta look like that. A B kind of goes bumpity, bumpity, capital B. See your fingers there? Everybody got that? Little B? So your 4 fingers are the magnetic field. Your thumb is the velocity of the charged particle, positive charged particle. Remember, everything in physics is based on little positive charges. So in a minute, we'll talk about, well, what happens if it's a negative charge? So for now, let's just leave it a positive charge. So your thumb is the velocity of the charged particle. the palm of your hand is the force. Okay? So let's do a problem. So let's say the magnetic field is traveling towards that back wall. Okay? It's going that direction. The velocity of the charged particle is towards the screen, like this. So in this situation, which way would the force on the charged particle be? So here, your four fingers are the magnetic field, so your four fingers should be that way. Your thumb is in the direction of the positive charge's motion. So which way is the palm of my hand? Up. The force would be out of the palm of my hand. That make sense? Now, what if the charge is a negative charge? Well, you got two possibilities. If the charge in the problem is a negative charge, number one, you could switch to your left hand. Look at the right hand rule becomes the left hand rule. Okay? So if it's a negative charge, the force would be down. It would be the other way. Or, what I prefer, you could stick with your right hand. But instead of the force being out of your palm, the force will be out of the back of your hand. Okay? So let's do a problem here. So we're going to end with this. All right, so let's say that we have a region of magnetic field. So these X's here, so what do X's indicate? In or out? In. So we have magnetic field going in, and then let's say we have a positive charge that's shot into that magnetic field region. Which way is the force on that positive charge going to be? Well, don't use your left hand. A left hand would be for a negative charge. Are you left-handed? No? The force. When this charge enters the magnetic field, so the velocity is that way. Which way is the force going to be?
Does it go your back of your hand, or it's like out of your palm?
It's out of the palm right here. The force is straight up. The force would be that way. Now here's why. Look. X's indicate in, so you put your four fingers into the screen, like that. The velocity's to the right. Which way is the palm of my hand? Up. So the force would be up. And tomorrow, what we're going to talk about is, look, if you have a force that's if you got a force that's perpendicular to the velocity of the motion, what's going to happen here? It's going to follow a circular path. If you think about it, think back to chapter 7 when we did circular motion. If a force is perpendicular to the motion of the particle, well, that means that the force is pointing to the center of a circular path, which means that that force is a centripetal force. So that'll be for tomorrow's lecture. Let's back this up. What if this charge that we sent into the magnetic field, what if this charge were a negative charge? Which way would the force be when it entered the magnetic field? The force would be down, because now the force would be out of the back of your hand. Okay? Hey guys, last question. What's the theta for this situation? Right? F equals QVB sine theta. What's theta equal to there? 90 degrees. And here's why. Let me just show you. Hey, it helps. When you're doing the homework problems, I highly recommend that you get, just use some pens. Just be like, all right, this red pen is magnetic field. This blue pen is the velocity, right? So you'd be like this. The magnetic field's going in, right, like that. Which way is the charged particle going? Like that. What's the angle? 90, right? That's 90 degrees. Okay, we're done.